And effectively, those particles combine to produce systems with confined quarks. So, as I said, this is rather inconvenient. Now, in fact, you could ask the question, how do we know they actually exist? Right? Well, one way we know they exist is that we actually see events like this at the Large Hadron Collider. So I'll just walk you through this. This is an event display from a proton-proton interaction. The protons come perpendicular to the beam. Okay? Now, what's shown here is there's an inner part of the Atlas detector, I'll say a little bit more about later, that essentially follows the particles as they come out. In fact, if you look really carefully, you can see little white dots in here. Okay? Those are actually measurements of where the particles passed. Okay? You see these lines? Those are our representation of where the particles went by connecting those dots together. Okay? And the particles bend because they're in a magnetic field, and charged particles bend in a magnetic field, and in fact the curvature of these lines has to do with the momentum of the particle. The straighter they are, the higher the momentum or energy, the more they curve, the lower momentum. Then, outside these detectors which allow us to track the particles are these things called calorimeters, which measure the energy of the particles. We have two kinds. The green is called an electromagnetic calorimeter. It is good at measuring the energies of photons and electrons, and in fact most of the energy of photons and electrons stays in that calorimeter. But then there's, behind it, another calorimeter that measures kind of everything else, right? And you can have events where the protons come in, and one quark from one proton scatters with a quark from the other proton, and they come out. Right? And when they come out, over short distances, they actually don't know they're supposed to be strongly interacting. Right? So they almost like forget that there's a strong interaction. And then as they get further and further apart, they realize, oh, we're supposed to be strongly interacting. And this process happens where they get further and further apart, and they start pulling a bunch of particles out with them. Right? And so that's what you actually see here, these particles and the energy in the calorimeter. They're what we call hadrons, created as two quarks come out from a scattering, and we have a technical term we call hadronized, but basically means they produce a bunch of particles. Okay? And notice they're exactly back to back. Okay? That's because momentum has to be conserved, and the protons coming in this way have no momentum in the plane in this direction, right? So there has to be zero momentum at the end, right? So these come out exactly back to back, almost. There's other things that go on, but I won't get into the subtleties. And they have to have pretty much the same energy. Okay? And there's a little Lego plot over here which shows the energy distribution in the calorimeter, and this one's a little bit more spread out than that one, but you can kind of see that these have similar energy. So this event happens because there were quarks in the incoming proton. The quarks scattered and turned into a bunch of particles. We call these things jets, because physicists love to make up names for things, and these are jets. So like jets of particles. One goes in one direction, one goes in the opposite direction. So we know they're there. In fact, this is an event. You're seeing, in a sense, the scattering of quarks. So why does this work, actually? Well, it works because the strong interaction is weaker at higher energies, right? The higher energy you go, the weaker the strong interaction gets, which is really kind of strange. Or, equivalently, at shorter distances. And remember how I said that, in fact, after the scattering, the quarks initially kind of forget that they're part of the strong interaction. I'm giving you kind of the non-technical version, right? But that's really what happens, and as they get further out, they start to interact more and more strongly again, and then they have to hadronize and produce all these particles. So we physicists figured out that this is the way the strong interaction should work in 1976. Okay? A few years later, people started thinking about the consequences of this and came up with a really crazy idea. Said, we can't see the quarks inside protons and neutrons, they're confined, but suppose you could do the following. Suppose you could take matter-containing quarks, subject it to extreme pressures, so you squeeze on it, heat it to about 1 trillion degrees. Okay? Could we create a plasma right, in which the quarks are no longer confined. Because after all, if the strong interaction gets weaker at short distances, if you can squeeze and heat up the system, maybe we can force the quarks to be at shorter distances such that they no longer are confined and they create a plasma. Okay, it seems like a crazy idea. I mean, a trillion degrees, right? But, okay. And in fact, we refer to that thing as a quark-gluon plasma. So here's a picture of a normal plasma, right? Normal plasmas are hot gases where the atoms are completely or mostly ionized, right? And you basically get a system of ionized atoms where it's all you've got is the bare nuclei and a bunch of electrons running around, right? And they're actually quite interesting, right? And this is people try to use these to study, or actually make fusion. But in fact, plasmas have really interesting properties and are a subject of study in their own right. And by the way, that's just electrical plasmas, not even the strong interaction. I mean, people have been studying these for basically 60 years, right? And we're still learning about how plasmas behave. So you can think about, right, how the strong interaction, as I said, is quite a bit more interesting than the electromagnetic interaction. If we could create a plasma governed by the strong interaction, if the electrical plasmas have turned out so interesting, what might happen if you could make a strongly interacting plasma? Well, here's an artist's rendition of what a strongly interacting plasma would look like, because you can't really see them the way we create them. Maybe this is mostly to show you this is an inside joke, right, which we physicists refer to the strong charge as color, and there are three kinds, red, green, and blue, and thus this picture. So there's the inside joke. This is an artist's rendition. I will show you a physicist's rendition in a second, but back to the early universe. This is a different picture of the evolution of the early universe as a function of time and temperature from the Big Bang and inflation all the way to where we are now. And, well, actually, as the temperature evolved, the kind of phases at which the matter in the universe existed also evolved. Okay, and around 10 to the minus 6 to 10 to the minus 5 seconds after the Big Bang, we actually think that the universe was in a state of this quark-gluon plasma. So if we could create it in the laboratory, we would actually be recreating the conditions, incredibly early universe, thus primordial, right? So when I talk about primordial matter, yeah, we're not quite getting back to there, but I would say 10 to the minus 5 seconds after the Big Bang isn't too bad. So how to do it? How could you create matter at a temperature of 1 trillion degrees? Well, in fact, back when I was just finishing up my undergraduate degree